Welcome to another exercise on the Simplex algorithm. Here we have a slightly larger text exercise with the following background information. Sandeman produces two types of ornate decorative wooden coffins, premium and deluxe. Each item produced goes through three manufacturing processes: cutting, sanding, and finishing. Each premium coffin produced requires 1 hour in cutting, 30 minutes in sanding, and 30 minutes in finishing. Each deluxe coffin requires 30 minutes in cutting, 45 minutes in sanding, and 1 hour in finishing. In the coming weeks, Sandeman has 40 hours of cutting capacity available, 14 hours of sanding capacity, and 60 hours of finishing capacity. Assume all premium coffins produced can be sold for a profit of $500 and all deluxe coffins can be sold for a profit of $400. Then we have two tasks to perform. First, formulate the respective linear problem, and second, determine the optimal number of each type of coffin to be produced to maximize profit. Well, since B depends on A, we're going to start with actually getting the information of the text into a mathematical formulation of the respective problem. This is what we're going to do here. We're going to start with the objective function. Well, we see here they get profit from selling their coffins. So as they would act like a normal company, they would aim for maximization of their profits. Well, they have two types of products which they are selling, premium and deluxe coffins. So we can say the quantity of premium coffins they are producing would be X1. The amount of deluxe coffins they are producing would be X2. Since they want to maximize profit, the respective objective function would be the $500 per premium and the $400 per deluxe coffin. So I multiply this with X1, this with X2, and add it up, giving me this objective function. Since 500 and 400 are quite large numbers, we can make it a bit easier by dividing the whole function by 100, reducing it to this version. Well, we have to keep this in mind for the simple reason that if we calculate the objective function value later on, and we have the value for the optimal solution, we would have to multiply this with 100 again to get back to the original formulation. Well, so much in advance on this. However, aside from the objective function, we will also have some constraints. In particular, we have constraints regarding the three processes all coffins have to go through: cutting, sanding, and finishing. Since we have some information in hours, some information in minutes, it would be easier to formulate everything in the same unit, so we're going to go with minutes. So we're going to reformulate this into 60 minutes, and here we're going to multiply with 60 in each case to get minutes. So we have 2,400 minutes, and 3,600 minutes of capacity. Well, then we can just go with the first part on cutting. So for each X1, we have 60 minutes cutting. For each X2, we have 30 minutes cutting. And the total amount of cutting used to produce the coffins should be less than 2,400, which is the 40 hours of capacity. Again, we can simplify this constraint a little bit. We see that all three numbers are divisible by 30, so we can divide by the largest possible divisor, which here would be 30. So it reduces to 2x1 plus 1x2 smaller or equal to 80. Then, well, we do the same thing for the second process, which is sanding. So we have 30x1, we have 45x2, and we have smaller or equal to 2,400 as well. That's exactly like this. Again, we can simplify a little bit. We cannot divide by 30 without having to resort to use fractions or decimal numbers. So here I'm just going to divide by 15, giving me 2x1 plus 3x2 small or equal to 160. Well, and finally we are left with the last of the three processes, finishing. So we have 30 for x1, we have 60 for x2, and we have capacity of 3600 minutes, which would look like this. Again, all of these numbers are divisible by 30, so we're going to divide whole inequality by 30, giving us 1x1 plus 2x2 smaller or equal to 120. Well, we're almost finished. The only thing we need are the non-negativity constraints, because we cannot produce any negative number of coffins. Well, so far so good for the first part. So using this, we can then start formulating our initial table to work with the simplex. For this, I'm just copying my problem. Then I'm going to build this table. For each of my decision variables, I'm going to add one column. And then, in addition, for the objective function, one row here. I call it Z for objective function. And for each of my three inequalities, I'm going to add one additional variable. So the x3 for the first, x4 for the second, and x5 for the third constraint. So far for the structure. Now we have to insert the numbers. Since this is a maximization problem, I take the coefficients from the objective function and I multiply them with -1. So I have -5 for x1 and -4 for x2, putting those numbers in the respective columns. Then the numbers up here have a value of 0, so I'm going to insert 0 and 0 for x1 and x2, giving me a result for this solution of 0 for the objective function, which I put here. Then, regarding all of my constraints, I need to have them in the form that they read smaller or equal to. Well, all three of them fulfill this requirement. So for all three, I can simply copy-paste the respective coefficients and right-side values. So for x1, I have 2, 2, 1, which I copy here. For x2, I have 1, 3, 2, which I copy in the x2 column. And on the right side, I have 80, 160, 120, which I copy here. This is my first initial starting solution. Before I can continue with the classical simplex, I have to check if this starting solution is actually feasible. To do this, I'm going to check the values here on the right side and see if they're all positive or 0. Well, here all of them fulfill this requirement. So my initial solution of 0, 0 is a feasible solution. Then I can start my normal simplex. Simplex means first I have to select pivot column. For this, I'm going to take a look here at the objective function. I'm going to select a column where I have a negative value, and this negative value out of all negative values is the absolutely largest. Well, here I have both of them qualifying because they're negative. 5, however, is larger than 4, so this is absolutely speaking larger. Well, so this gives me x1 as pivot column. Then I have to select pivot row. For this, I consider all rows where I have in the pivot column a positive number. Well, here, a positive number for all of them. So all 3 rows qualify for pivot row. To decide which to take, I'm going to take the right-hand values, divide them by these values. So I have 80 by 2 is 40. Here I have 80. Here I have 120. And then out of these 3, I select the one which resulted in the smallest outcome, which would be this one with 40. So this becomes pivot row. This was pivot column. So the 2 is my pivot element with which I'm now going to work and do my simplex transformation. This is what I've prepared in this table. So first off, I'm going to exchange the two variables in pivot row and column, those two. And then for the pivot element, I'm going to replace it by 1 divided by pivot element. Everything else in pivot row, I'm going to divide by the pivot element. So 1 by 2, 80 by 2. And everything in pivot column, those 3, I'm going to divide by minus the pivot element, so by minus 2. So minus 5 by minus 2, 2 by minus 2, and 1 by minus 2. That's the easy part, getting these row and column done. Now I have to calculate all the other values. For this, I'm going to use a rectangle scheme, which works as follows. I consider the number I want to change. For example, here this, or recalculate, this minus 4. Then I take this as one corner of a rectangle and the pivot element as the opposing corner, giving me this rectangle. And then I do the recalculation the following way. Original element minus this corner times this corner divided by pivot element. So here, minus 4 minus minus 5 times 1 divided by 2. Well, I have minus minus, so I have plus. Minus 4 plus 5 half. So minus 4 plus 2.5 gives me minus 1.5. I'm going to do this for all other values. For example, here, 0 minus minus 5 times 80 divided by 2. Minus minus again gives plus. So those two multiplied is 400, divided by 2 is 200. So here I have 0 plus 200, giving me 200. And I'm going to do this for those 4 as well. So for the 3, working with this rectangle. So 3 minus this times this divided by this. For this 2, working with this rectangle, 2 minus this times this divided by this. For the 160, I have this rectangle, 160 minus 2 times 80 divided by 2 gives me 80. For this 120, I have this rectangle, 120 minus 1 times 80 divided by 2 gives me 80 as well. So this way I have recalculated the whole table and can take a look whether I already arrived at the optimal solution. For the optimal solution, all entries here in this objective function row need to be positive. This one is positive, this one is not yet. So I'm not yet at the optimal solution. Well, then I can repeat my pivot selection process. I'm going to select a column where I have a negative entry in the objective function row. So, well, this is the only one. So x2 becomes pivot column. Then I observe all values which are positive. Well, all 3 qualify. And again, divide right-hand side values by these ones. So here I have 80, 40, and here's something which is slightly larger than 40. Well, 60 as well. Once I'm finished, I select the row which yielded the smallest result. That's why I do not have to do this here in detail. It suffices to see that 40 is by far the smallest one. So x4 becomes pivot row. This is pivot row. This is pivot column, giving me this 2 as pivot element. And with this, I'm going to do my new recalculation. So I'm going to copy this table here. And then, as I said, do the simplex transformation. I'm going first to switch pivot row and column variables, so those 2. For the pivot element, I go 1 divided by pivot element. Everything in pivot row, I'm going to divide by the pivot element, those 2. So 1 by 2, 80 by 2. Everything else in pivot column, I'm going to divide by minus pivot element, so by minus 2. So this by minus 2 gives this divided by minus 2 gives this, and this divided by minus 2 gives this. So far so good. For the rest of the values, so the other 6 values here, I'm going to use this rectangle form again. Now, however, I can perhaps save a little bit on time. I'm going to start with this value here because I know this one is already positive. So if I start with this value, I have this rectangle. So here I'm going to go 2.5 minus 1.5 times -1 divided by 2. So minus, 3 minuses, 2 cancel each other out. I'm left with 1 minus. So it's 2.5 minus 1.5 divided by 2. So 2.5 minus 0.75 gives me 1.75. This is positive. This is positive. This shows me I have arrived at my optimal solution. For the optimal solution, I do not need the values here in this part, and I only need the values, those two, for my decision variables. Well, I already calculated this one, so I have to do the recalculation here with this rectangle. So 40 minus 1/2 times 80 divided by 2, which is 40 minus 20, giving the 20 here. And I have to get the value for the objective function, this value here. So I'm going to work with this rectangle. 200 minus 1.5 times 80 divided by 2, which minus gives plus. This is 60, so 200 plus 60 gives 260. I could calculate that one, but I not necessarily would require it to be calculated if I'm just interested in the optimal solution, so in the x1, x2 values. Well, here if I do this, I have this rectangle I'm going to work with, and in the end I will end up with this table. Well, how to interpret this solution? As I said in the beginning, everything up here is 0. Everything here has those values on the right. So my optimal solution is x1 is 20, x2 is 40. Since I had premium and deluxe coffins, I have to produce 20 premium, 40 deluxe coffins, giving me this value for the objective function, this profit. But now I have to remind myself I have divided the objective function by 100 to make it easier. So I have to multiply this again with 100. So my profit is not $260, but I have to add 2 more zeros, multiplication by 100, giving me $26,000 as profit. So far so good for the optimal solution, but this table tells me one more thing. Those variables up here, they are 2 variables for constraints, similar to the x5. Since they're up here, they have a value of 0. This indicates that those inequalities are fulfilled with equality. Well, it could be small or equal to, so here the equal to holds, meaning for whatever x3 and x4 represent, I'm going to use the maximum. Well, those were the 2 parts of processing, so the cutting and sanding. So I used my maximum of 40 hours I had in each of those 2. For the x5, the finishing part, I have the variable down here. I have a value here. This means I still have some buffer. That's actually the buffer. So I'm not using the full 3,600 minutes. I'm only using 20 minutes less. So I have a buffer of 20 minutes in the finishing process. Well, that's then everything I could get from this table. This brings me to the end of this session, which I hope you enjoyed, which I hope you learned something from. I say goodbye and see you next time.